In this video, we're going to discuss the relationship between thermodynamics and redox reactions, or more specifically, the relationship between the free energy of a reaction, delta G naught, the standard free energy, and the electromotive force, or standard electric potential, okay, of a cell. Because we have said that electrochemistry, okay, is the relationship between chemical energy and electrical energy. So today, this video is going to allow us to relate chemical energy to electrical energy very directly. So let's say we have this cell below. We have solid magnesium reacting with silver chloride to produce magnesium chloride and pure solid silver. So first review, let's figure out what's getting oxidized and reduced and write the half reactions. So magnesium, solid is 0. Silver and chlorine, chlorine's -1, so silver must be +1. Here, chlorine's -1, I have 2 of them, so magnesium must be +2. Here, silver solid, it must be 0. So if I track silver, it's going from +1 to 0, so it's getting reduced. Whereas magnesium is going from 0 to +2. The oxidation number is increasing, so it must be losing electrons, so it's getting oxidized. So to write my half reactions, first for magnesium, Mg solid. If it's getting oxidized, that means electrons are lost, so they're going to be products. Is becoming Mg2+. Now I have to think about how many electrons. Well, since the charge is 2 and it started at 0, 2 electrons transferred here. I didn't write the chlorine because the chlorine's a spectator ion. It's not participating in the reaction. It's not getting reduced. For my reduction half reaction, I'm going from silver, Ag+1, from here. And since it's getting reduced, it's gaining electrons to produce Ag solid. How many electrons? Well, since I'm going from +1 to 0, only 1 electron is needed. So those are my 2 half reactions. Again, this is my reduction, and this would be my oxidation. Okay. If I wanted to calculate the voltage of the cell, I would need to use this information up in the orange table here. E naught of the cell is what's getting reduced plus what's getting oxidized. So my reduction, which is my silver, 0.80, plus what's getting oxidized, which is magnesium, so I flip this sign, positive 2.37, so I get a voltage of 3.17 volts. But now what I want to know is how can I use that to figure out how much energy is getting transferred, the free energy, delta G. So the relationship between those 2 values comes down to one equation. And that equation is here. The standard free energy of a reaction, delta G naught, is equal to negative NF E naught of the cell. Okay? This is the equation that we need to know. It's on your equation sheet, but let's just break down everything that's in here. Delta G, this is the free energy, which we learned. Units of kilojoules per mole are how they're usually expressed. E naught of the cell. Okay, this is the electromotive force, EMF, measured in volts. 2 new variables here. The N is the number of electrons transferred in the reaction. Or more specifically, it's the moles of electrons that are transferred in the reaction. So we will get this from the coefficients in front of the number of electrons. The new variable that we've never seen before, okay, is this one here, F. This is Faraday's constant, named after the scientists who made this relationship known. Faraday's constant is 96,485 coulombs per mole of electrons. So, more specifically, I guess this should say mole of electrons. So again, C is a coulomb, C-O-U-L-O-M-B. A coulomb is a unit of charge. Okay? So one electron, is a negative charge. We can measure the amount of charge of that electron in coulombs. If something's positively charged, we can measure what the charge of it is in coulombs as well. What you need to know is anytime you use F, Faraday's constant, you need to plug in this value, 96,485, which has units of coulombs per mole of electron. That is also on your equation sheet in addition to this equation. Now, how do we use it? Well, let's consider that reaction back from the very beginning, from the very first page. Okay? I'm just going to rewrite the half reactions here. We had Ag plus an electron makes Ag. And we had magnesium getting oxidized to form magnesium 2+ and 2 electrons. So what we notice is if we combine these two equations together, they're not going to balance out. They're not going to balance out because I have 2 electrons in the product on the oxidation reaction and only 1 in the reactant of the reduction. So what I need to do in order to cancel these out is multiply this times 2. So now if I add these reactions together, I'm going to get 2Ag plus magnesium forms, plus 2 electrons forms Ag plus Mg2 plus 2 electrons. Now, these electrons cancel out, so I'm left with the original reaction that's up above, except without the chlorines, because they're spectator ions. Why did I do all that? Well, if we remember the equation, okay, delta G naught equals negative NF E naught of the cell, I need to know what N is, the number of moles of electrons that are transferred. So you might have looked at these half reactions and seen, oh, only 1 electron is transferred. Or you might have looked at it and said, oh, only 2 electrons are transferred. In order to figure out what N is, we need to figure out the total number of electrons that are transferred, which needs to be the same in both half reactions. So that's why I had to multiply this by 2. So I'm going to plug in 2 for N. Why am I doing this? Well, the question is asking for the reaction below. What is the change in free energy? Delta G is what it's asking for of the cell. Remember, we already calculated E naught. If you hadn't, you would need to, but we already calculated at 3.17 volts. So I'm just going to plug in my numbers. Negative 2 times 96,485 times 3.17. The answer that I'm going to get there is going to be in joules. Negative 611.714.9 joules per mole. So I'm going to convert that to kilojoules by moving the decimal over 3 times. So negative 611.7 kilojoules of energy. Now let's pause and think. Does my answer make sense? Well, E naught was a positive value, greater than 0. So that means spontaneous. So what should I know about my delta G? Delta G needs to be less than 0. Aha! Delta G is negative. So my answer makes sense, spontaneous reaction. Let's do one more example. Calculate the change in free energy, delta G naught, for the reaction below. Okay, a little typo here. Here's my reaction. So what I need to know first, if I have my half reactions, is what's getting oxidized, what's getting reduced. So aluminum is going from 0 to positive 3. So I know that aluminum is getting oxidized. That means that bromine, which is going from 0, diatomic, to negative 1, is getting reduced. So if I wrote my half reactions, okay, for aluminum, all right, aluminum, if I wrote the half reaction for aluminum, it's Al oxidation, so loss of electrons to form Al plus 3 electrons here. And my reduction half of the reaction, Br2, must be gaining 1 electron to form Br minus. Now, here's the thing. This is not balanced, this half of the reaction, because I have 2 bromines here and 1 here. So I need to balance it. So I need 2 bromines here. Well, if I had 2 bromines, now I have negative 1 bromine, but 2 of them. So I'm going to need 2 electrons to make this balance. So now if I look at my 2 half reactions, can I add them up to get them to cancel out? No. 3 electrons, 2 electrons. So I'm going to need to multiply this by 2, and I'm going to need to multiply this reaction by 3, because that way I will get a common value of electrons. So now if I add the reactions together, I'm going to get 2Al plus 3Br2 plus 6 electrons makes Al3 plus 6 electrons plus 2 Br minus. My 6 electrons cancel out. I know that's going to be my value of N. Delta G naught equals negative NF E naught of my cell. So I'm going to plug in negative times 6 Faraday 96485 times the E naught of the cell. Oh, haven't calculated that out yet. Got to use this information. E naught of the cell is going to be what's getting reduced plus what's getting oxidized. So what was getting reduced? We said the bromine. So 1.07 plus negative 1.66, flip the sign, 1.66. That's going to give me a voltage of 2.73. So now if I have that, I can plug my voltage down in here, 2.73. And then if I go ahead and do the math, if I multiply all those numbers across, I get a final value of, if I convert to kilojoules, 1580 kilojoules. Except it's a negative. So, does my answer make sense? I have a positive voltage, so this is spontaneous. I have a negative delta G, so this is spontaneous, so this makes sense. What you need to know from this video is how to use this equation, what each value represents, how to write your half reactions like so, how to balance them if needed, like we did here, and then getting your final answers.